So this week we'll talk about contactors and relay. Those are contactors and relay, and this will be your friend in control all the way until you graduate. And when you do a lot of troubleshooting, you're always going to have to deal with contactors and relay. What is the main purpose of contactors and relay? They are communication between two circuits. Bless you. Change from one low voltage to high voltage. Basically, it's for control. So one circuit will turn on a switch, and the other circuit will connect. So if you look inside, they have switches between them, and those switches do connect. And for the lab, I will have you draw schematic for this control, even though it looks kind of ugly now. But after I promise you, within 20 minutes, you'll know how to draw schematic for the entire thing. Just by simple logic of following a circuit. We'll do it together, and that's tomorrow. But for now, I want you to think about contacts and relay and know what is the purpose of contact and relay. They open and close set or sets of electric contacts by an action of a solenoid. What is a solenoid? It's this piece here. Let me show you. So that is a relay. Never sneeze, never sneeze. Okay. Not gonna happen. So this is my coil. What is it? What do you think this coil does when it gets energized? It's become a magnet, and it will pull this in. You will see this get sucked in, and when it gets sucked in, you see those little knobs over there? They connect, and if you look at those little knobs at the bottom, they connect here, and they close the circuit. So this circuit connects, and those two little contacts get together. We have two of them. One of them is going to pull in when we need hot water, and the other one will pull in when we turn on the circulator. So those two control two other circuits. This board will have the thermostat come to it, will close the circuit. It will tell this board to energize. This board, even though as simple as it is, this one's complicated actually. Let's get a simpler one. Okay, much simpler. One relay, transformer, and a switch. This switch is connected with a bulb. This one has liquid inside. You stick this inside the hot water tank. This will gauge the temperature, and based on that, you put your set temperature here. It will open and close a circuit. Okay, so this contactor here will get pulled in once the thermostat is calling for heat. If you jump for this, meaning putting wire between them, it will think the thermostat is closed, and it will activate the board. The board will close the circuit, but also it will check another input, which is the water temperature. If the water is hot, it will turn on a pump and circulate water. If not, it will energize the board. This is the back of it, and those little grooves are just wires, are just connections. So we're gonna be friends with this. It's called an aquastat. For the next few months, we'll be friends with it, know how it works. We'll know every moody situation you can get into, what could be wrong with it. And again, this was the basic of controls. It has evolved a lot since then. Now it's just a board, we don't see much, but knowing the mechanical part will help you understand what's happening in there. So those are relays. Relays are small. Who can tell me what is the difference between a contactor and a relay?
Contactors are big, they're bigger.
Bigger? That's true. This is a contactor. It does the same thing. What else? What is the main difference? They are bigger. Amps. The amount of voltage that goes through them. It has to be more than 20 amps. I guess for technicality, it's a relay on steroids or something. You know, it's just the same thing. It's just a technicality. I basically do not care, but the book wants to know, and somehow technically it makes a difference. contactor is bigger and has more than 20 amps going through it. So if it has more than 20 amps, where would you find that? Usually in air conditioners, where the compressor is outside. When you hear it loud click, so I'm gonna turn on the AC now, and you're gonna hear the loud click. That's a contactor over there, and that's more than 20 amps. And now, hear that? Click, click. And that's a contactor. So if you guys remember that, contactor is a relay that's more than 20 amps. You can just forget the rest of the class. Doesn't matter. So when the solenoid is energized, it closes a set of contacts. Main difference is the size of the size, not the physical size, but the size of amperage goes through it. It has a bigger magnet, has to pull strongly two set of contacts, and simply a large relay. That's what it looks like. You have some examples here. If you look here, this is your coil, and these are the contacts. Little small semi-spherical pieces of silver and platinum sometimes for easy contact. They do get dirty sometimes, you have to clean them. So that's one. Contact and relays, they are composed of parts. Let's list those parts. 3 basic parts. That's really low tech. Contacts. That is this part. That's the contact. Then we have our coil. That will pull this in to open or close. Are they always stuck together or apart?
Depends on the solenoid, right?
Depends on the situation. Could be normally closed or normally open. What does the term normally means? Normally,
In the
Wait.
off position.
De-energized.
de-energized. The contact state when the control is de-energized. When you unplug it, is it normally open or normally closed? Some of them are normally open, some of them are normally closed. Some of them will be double throw, one will close, one will open. It will switch back, depending on what you want to do. So this is the pull set of contacts. These are the contacts. Coil surrounds the coil. And this is what they call mechanical
De-energized.
What's that right before? What's that? It's the blank is disenergized? The what?
control. Need a binocular from there. Okay? Symbols. Usually, whatever is sketched on the relay is when it's de-energized, which is the normal state. So normally, it's the position when the set of contacts of the device is de-energized. Normally open, when it's de-energized open. So this is normally open. So this is a really bad schematic. It should be touch. Okay. So this is normally. It's normally 2 L's or whatever. Closed. Normally closed. Okay? How would it look like in schematics? So we're gonna also look at reading basic schematics soon. It is very, very essential to be able to look at schematics and not be scared. It's very simple. It's like reading a map. Does anybody read a map anymore? Besides Google Maps. Can you find your way using a paper map? Come on. So what do you do with the first thing you hold the map?
Where are they from?
Figure
That's why you get lost. Huh? Thank you. First thing you find the orientation. You're gonna find north, then what are you gonna find? Where you are, thank you. Then what do you find?
Where you're gonna go.
Where you gonna go, and also basic landmarks. Dead reckoning, they call that dead reckoning. So you know where you are. So same thing is gonna happen with schematics. There's still no app for schematics, huh? You still gotta read schematics by hand. So first of all, what is your north? What is your north? Thank you. Energy coming in. Line 1 and neutral. That's gonna be your north. I'm gonna find what's the source. This is your north. Then you find where you are. Look at components. Look, what is this? What the hell is that? Randomize things, and it's gonna be very, very tough because things look differently. It's not gonna look like that. It's gonna look like some kind of symbol somebody thought that should represent the relay. So then what do you find?
Legend?
Thank you. You don't read math, man. How old are you? Probably my generation. You're Gen Xer, aren't you? Millennials, they have no idea. So, there used to be a time when we actually pull out the atlas when we try to go somewhere. Yeah. And this is how I got lost, looking for a restaurant in Springfield, Illinois, thinking it's Springfield, Massachusetts. I mean, so anyway, so this is what we're looking for. This is what looks like a relay most of the time. So it does not look like that at all. Right. So it's gonna be, in the map, this is gonna be a relay. And this is what it's state, that's normally open, that's normally closed. That's what it looked like that's the coil. This is more like a coil for me, or this could be a coil. I'm gonna pass some of these through so you can just like look at it and look at your future. Don't be scared. Seriously, that's why you're gonna make a lot of money. Because people are afraid to look at these things, they don't want to touch it. So you have the experience, you've been tortured to know what it means, and you can have the patience for it. Okay? So we know a relay, we know a contactor, what's a magnetic starter? So we have relay, here we have contactor, so contactor is a relay over 20 amps. Magnetic starter is a contactor with overload protection. It's a huge thing for big motors, more than 20 amps. Where you want to have some kind of safety. If you exceed the overload, it should trip by itself. And this is what it looks like normally. And it's very huge. And you will reset it by pushing those buttons down. So it will pull out whenever like you have excess load.
Assuming that schematic is how they're wired up.
Yeah.
What are the half circles?
It's just symbols for the what it looks like. The whole thing is a magnetic starter. Probably it's three phase.
Oh, are those for the screws?
No, this is actually just schematic for the wiring. For it's the three phase. 3 lines gonna go through it.
Okay.
So you're gonna have three-phase power going through it, 1, 2, and 3, and one neutral or ground. This is how they are wired, and that's the whole magnetic starter. That's what it looks like. So, let's have the schematic. That's what they look like. If you look on the relay I gave you, you see inside they have this kind of schematic. Okay. So we covered motors, we covered relays. Ah, it's you. Coronavirus. I'll take it. I will not be defeated by single cell organism. Switches. So switches and relays. We have relays. Relays communicate between two circuits. Switches you have to turn on manually. So switches, simple as that, on and off. This is disconnect switch for big power. We're doing a lot of manual work, and they have a lock. And I showed you what it looks like. That's I'll bring a disconnect switch. So that's a disconnect switch. Every equipment you install outside the house must have a disconnect switch right next to it. Why? If anything goes wrong with it, somebody has to be able to disconnect the equipment right away and have to go for the power panel. So this is a big disconnect switch, opens up when it's off, and you can lock it so nobody will turn it on. Disconnect switch. This is old days timer and relays that was installed on industrial boilers. This actually is a timer, a cam timer, mechanical cam timer. It's really a piece of art. Sure, it's okay. I can break it. All right. So switches. So these are on and off manual. These are pull down. These are toggle switches. So basically inside is a relay. You press on it until something else presses in the other direction is not going to activate. Kind of like the elevator. Back in the days, the elevator board was a bunch of relays. So you hit the relay, you engage the coil. The corresponding coil for that floor, it's not going to be activated till you reach that floor. So you go there and deactivate the magnet.
You still have them.
Yeah, they're still there. They're still there. They're very, very reliable, very effective. And they're gonna be happy too. So switches. Important term. Disconnect switch. Over there. Push button switches. You hit it once, they can hit it twice. They do single action. Thermostat is considered a switch, but you do not, it turns by itself. You set it, but it will turn on and off by itself. Also, pressure switches, they do turn on and off the circuit. Those are also considered switches, and they're also controlled. So thermostat and pressure switches are also considered to be switches. What would a switch look like in the schematic? Something like that. If you look in your book in chapter 6, you'll see a long, big page of all those symbols. You don't have to memorize all of them, but you'll make life a little bit easier to know the basic ones. And eventually they will stick in there. So, I think it's in the beginning of chapter 6. Yes, page 114 if you have this edition. These are all the symbols you might need for the HVAC. Some of them look intuitive, some of them you can try to understand how they work. And when in doubt, what are you going to do? If if you are writing schematics, put a circle and write what's in there. Put a circle and put right inside motor, compressor, switch, whatever helps the reader understand what's in that board. Of course, if you can't draw a resistance or a switch, the person after you will think that you're a rookie. So it's good to have the symbol correctly, but it's not that difficult. Of course, they come with practice. Pressure switches, that's what they look like. It's actually newer ones. So basically, they open or close a circuit based on low or high pressure. So this is high and low pressure at the same time, so it maintains the equipment within that set pressure. So either for steam boilers or in a power plant, you're going to have those pressure switches. Also, you will have them in big air conditioners unit, like heat pumps. You're going to have pressure switches. Why? Because we are afraid to exceed the design pressure in that refrigeration cycle, and that will cause us to what? Break the compressor. And that's the most expensive part of your equipment. Look here. So this is a complete AC. Got it out. So look, this is my compressor. This is low pressure switch, high pressure switch. These two are for safety to prevent the compressor from running under outside pressure. So this actually resembles a whole AC. You can look at it, and I can turn it on. You can see the superheat and subcool as well. So looking at that will help you see the pressure. And see, this is how this is wired. This will disengage the compressor if you reach the high pressure or low pressure, and you can set that with a screwdriver. So this high pressure is set at 250 psi. It will shut off the system. This for low pressure. If it runs at low pressure minus 20, which is vacuum, it will shut off the compressor. Otherwise, the compressor will malfunction. So those are put for what? For safety. So safety switches, and you also find those in power plant. And this is what it looks like in the schematic. Again, it looks very nice and simple and easy, but we'll look at some schematic that looks a little bit more involved. Safety devices. So again, pressure switches are safety devices. Thermal switches are also safety devices. We're trying to protect the circuit from doing something that we don't want, which is explosion, fire, spark. We don't want that. In the shop, we have GFCIs and circuit breakers everywhere. If you, God forbid, put something the wrong way, you'll maybe see a spark and something will trip right away. If we don't have those safety devices, probably it will be more dangerous. But today we tripped a fuse almost like 7 times. The ground was activated, neutral was put where hot should be, so it's good to have some safety devices. So fuse is the simplest way for overload, to protect against overload, effective against large load, but less effective against small overloads because again, they might not be able to detect it. What does a fuse do? Fuse, how does it function? Come on.
Burns out.
Burns out. Your car, don't you have a fuse box? It goes out sometimes and you change the fuse without even fixing the problem. And you go over again and you change the fuse and you buy a box of fuses in your car and you just keep changing them. No. The fuse is there to protect against an overload. So if the fuse goes out in your car, probably you have to go and check what's wrong with that circuit. There's a fuse for every single circuit in your car. There's actually 2 fuse boxes. One under your steering wheel for the easy stuff, lights and small loads. The big loads ones are under the hood because they don't want it to overheat and do something, melt on your feet or something. So it's very big load. Like for example, your wipers, big motor that's outside. Your AC has a fuse, it's in the outside, big fuses, and they have relays. And that's the first thing you want to check when something doesn't work in the car. There's so many electrical systems in your car. If you understand how your car works, you understand a lot of things about HVAC. You have a complete HVAC system in your car. Very simplistic, but it's very similar to what we do at home. What is your heat source in the car? Your engine. Your engine is a big heat source. That's actually the only free thing you have out of your car is heat. You have excess heat that you have to dispense with. So So if you can find a way to use that heat effectively, you can improve the efficiency of the engine. Anyway, thermal overload, they are operated by heat. They have bimetal, and also they disengage the system mechanically. Open a switch when it's too hot, does not melt. And magnetic. Magnetic is the same way. So we said again, when we run current through a wire, two things happen to it. It will create a magnet and also overheat. So we can use the heat to bend it over. Metals, when they get hot, they expand, right? So we can use that expansion to disconnect the switch. Or we can use this as a magnet and pull the contact out. So either heat or magnet, depending on the current, depending on the situation, you can have either. It can be like thermal switch, where it's like bimetal, it will break the circuit. Probably you have those on motors, where you want to use the heat or the magnetic side. Sometimes you have both. Okay, these are the fuses that you see around you, and they are rated by the amount of power that goes through them, from very small to fraction of an amp to all the way to 15 amps. And there are cases where we want to use fuses and not magnetic starter. For example, so when we work with motors, we want to use circuit breakers, things that can be reset, because it's very often that they have locked amperage drop. They get locked, so get a lot of some resistance to pull more temperature. In the lab, when we did the motor testing last week, and I put the screwdriver in the motor, you can see the amperage draws getting increased. When you turn on your AC in the summertime, you can see the lights dim for a slight second. It's drawing all the amperage from the house. So again, this is possible. This is very frequent. If you have a fuse, it will melt, and you have to go and change that every time this happens. And it did happen a lot in the past until somebody came up with a better design. So we used to have this old big ACs, 220 volts. You turn them on. If the compressor gets stuck or upset, it will blow a fuse. The fuse is in the switch. And the switch has a box full of fuses in it. So you go and change the fuse.
That's a lot of calls.
Yeah.
For,
Yeah.
for an approval.
Well, they teach somebody to do it. Luckily, I was appointed. And you go, that was very dangerous. But anyways, so if you come with a small piece of paper, you're very, very careful to put it in there because the whole thing is wired.
Oh, yeah.
Yeah.
Oh, you can disconnect those?
No, this kid.
Well, not disconnect it, but
Safety
turn
was
the power
completely.
Oh,
I felt like a plastic surgeon putting the fuse in and trying to screw it inside. And,
out the window.
yeah, so that, luckily we don't do that anymore. Yeah, we came up with a lot of safety devices now. We don't have to do these kind of dangerous things anymore.
Well, I'm sure a lot of injuries occurred.
Yeah, a lot of burnt fingers and watches and rings and stuff. It happens more than you think. Okay. Transformers, what do they do? Besides defending the galaxies, all this fun stuff. This is a transformer. It does. Come on, what does it do?
What is that?
Huh? That's what it looks like in paper. It's a transformer. What does it do? A transformer, step up the voltage or decrease the voltage, right? You have it in here. It's a transformer. So it's always going to either increase the voltage or lower the voltage using induction. If you look here, there's an iron core with induced magnet in it, and there's two winding, one for the low voltage, one for the high voltage. The more winding you have, the more voltage you get out of this iron core. So for example, in my huge transformer here, that costs a lot of money. Someone else. You can change the voltage from 110 to 10,000. How much are we changing this little board? From what to what? What is the incoming voltage? Jesus. What voltage gonna power this board? 110. Excellent. What volt? And we see also thermostat. What voltage coming out going to the thermostat? Huh? Yeah. So 24. So I know this transformer is supposed to change 110 to 24. That's why we have a transformer there. So that's what it does. It changes usually from 110 to 20 to 24, and so on. Our time goes fast when you're having fun. Okay. How much we have left? Almost there. Want to start the video?
Huh?
You pause it?
Have we?
Yeah.